Okay, good afternoon. So let us start a lesson. A primitive function. First of all, I want to define what a primitive function is. So I write definition. So do you remember something from Math 3C? Yes, we say that a function, and usually we denote it with capital letters, a function capital F is said to be a primitive function of a function little f if, okay, do you remember what is that? If what happens?
Was it the derivative of capital F?
Yes, is equal to little f, yes.
Yeah.
Of course, the very precise mathematical definition is a little bit subtle than that. You need to also talk about the domains and things like that, but you don't need to be worried about for this course, or about those things in this course. So that is actually my primitive function, yes? So that was the notion we defined here. Okay, so let me give a simple example. All functions say, for example, capital F sub 1x, x to the power of 3, f sub 2 of x equals to x to the power of 3 plus 2, and f sub 3 of x is, say, for example, x to the power 3 minus the square root of 7, are primitive functions of the function f of x equals to 3x squared, yes? So let me write, since, why this is true? Because if I differentiate capital F1, or if I differentiate capital F2, or even if I differentiate capital F3, all of them are equal and also equal to the little f of x. Yes? It's very clear. If I ask you what is the derivative of this function, it becomes 3x squared. If I ask you what's the derivative of that function, the same answer, and the same thing for this one. So at least something is clear. When you find a primitive function, you in principle find infinitely many of them suddenly, yes? So if I give you x to the power of 3 is a primitive function, you can immediately add or subtract the constant from that function. Still you generate a new primitive function, yes? Is that understandable? The idea is very clear, because if capital F is a primitive function, so let me just, this is a simple remark, so let me write it here. So if capital F is a primitive function of say little f, then that function capital F plus any constant where c is an arbitrary constant is also a primitive function of f. Okay, if someone asks you why, the answer is very simple. Yes, because what you do capital F is a primitive function for f. What does it mean? It means that I already know the derivative of capital F is little f. My goal is to show that if I add any constant to the capital F and I differentiate it, it is clear. It becomes what? It becomes f prime plus c prime, but f prime is little f, but what is c prime? Is 0, yes? And I get the same thing. So that part of this remark, actually this remark is trivial, but there is another non-trivial aspect to this remark, and that is the reversed problem. So if I know that the derivative of two functions are the same function, I can conclude that these two functions differ by just an additive constant. The answer to this is, under some conditions, yes, and then the proof is beyond the scope of this lesson, so you have to wait for some other tools in higher mathematics to be able to prove this simple idea. So, but let me just write this one as also a remark. So let f prime of x be equal to g prime of x. Of course, there is a big if here. As I told you, you don't need to be worried about that if f and g are defined on an interval. Okay, so forget about that part. But let f prime of x be equal to g prime of x. Then what happens? The difference between them is a constant, or you can say one of them is equal to the other one plus a constant. Yes? Then we can say there exists, so this means there exists a constant, such that what happens, such that the difference between these two functions is equal to c, or you can say one of them is equal to the other one plus that constant. Yes? This part of the this is not that trivial. That if the derivative of two functions happen to be the same, they have to differ by a constant. It is very trivial that if they differ by a constant, the derivatives are the same. But there is no guarantee that if the derivatives are the same, they also differ by at most an additive constant. Yes? You might, because you know that differentiation is a little bit complex process, so you might say that, okay, how we know that if the derivatives are the same, there are not two completely different functions, so that when I do differentiation on one of them and do differentiation of the other one, for some strange reasons, terms cancel out and then I get the same answer. This theorem guarantees that don't worry about those situations, this is not going to happen. Of course, if f and g are defined on one single interval, okay, but don't worry about that. Okay, so let me first give you a little bit more advanced example. So let me write example here. I would say show that capital F of x equals to ln of x plus square root of x squared plus 1 is a primitive function of f of x equals to, if I remember, yeah, it is 1 over square root of x squared plus 1. Okay, so I want you to differentiate between two problems. This problem, I don't consider it very hard, yes, Because I have already proposed you the primitive function, and I'm asking you to investigate if it is true or false. The hard problem is not this question. The hard problem is if I give you this function and I ask you find a primitive function for it, that's completely different story. Yes? So I want you to first of all differentiate between these two level of problems. Okay. So if a proposed function is if a primitive function is proposed to you for a function, if you want to show if it is true or false, you just need to do differentiation of the proposed function to see if it works or not. Okay? It might be a hard function to differentiate, but that's not a big problem, because if you have practice enough for differentiation, that's not a big problem. Okay? But I want you to understand, if I haven't proposed this, by the way, let us imagine I haven't proposed this to you yet. I give you this function and I ask you find the primitive function for this. You might even not guess it is logarithmic function. Yes, because that's a square root function, 1 over square root function. I'm asking you to give a primitive function for this function. Okay, and this problem, if correct, is proposing one logarithmic function for this one. And then, by the way, you might say that, okay, might be there is also a trigonometric function with that property. Do you think it works? Yeah? Do you think you can find a polynomial function or a logarithmic function that is also a primitive function of that? I want you to tell me because of that content. The reason that I'm asking this question, I want you to understand the content of the remark. The answer is no. Because we just showed that if two functions happen to have the same primitive function, they can at most differ by an additive constant. So there will be no polynomial function, a primitive function for that, because a polynomial function and a logarithmic function does not just differ by one constant, they differ quite a lot. They're completely different things, yes? So this means that more or less the only function that you can imagine which is a primitive function of this one is just the one that I propose in the problem, or at most that one plus a constant. That's it. Okay? So let us now solve it. But I mean, this has nothing to do with your skills in primitive functions. It is a practice in an indirect way in differentiation. So what we do, so we start differentiating the function. Do you remember what is the correct rule of differentiation here? So I need to investigate if capital F prime is equal to f of x. If the answer is true, it means that we actually are done. So do you know what formula helps me to differentiate this? No, because don't think here. You are supposed to differentiate this one.
Product rule.
No, that's not a product. ln of something does not mean ln times phi. ln of something is the whole thing itself, yes?
Chain rule?
Yes, chain rule, but which formula? Combined with the derivative of ln formula. So you need to remember it, hopefully. So do you remember what was it? ln of a function, say u prime. What is that? It is 1 over u, but multiplied by u prime. So this is the formula we had when I was teaching you the derivative of a logarithmic function. So I want to use that. I want to give the role of u to this guy, yes? And then use that formula to differentiate ln of u. Okay, so let us start. So f prime of x is equal to, it becomes 1 over u, which is x plus square root of x squared plus 1, but you have to multiply it by the derivative of u, yes? Yes? Okay, so I have to continue. I copy and paste the first part, but I have to continue until I do not have any primes left. Okay, so that's also easy. The derivative of x is 1, but the derivative of this one, I want to use another formula. So what that formula is now, I have a square root of u, do you remember? Prime is what? Is 1 over 2 square root of u multiplied by u prime. So that is also another formula here. So I have to use that one as well. So what's the answer? This becomes 1. So if you don't mind, let me write it here. So let me take this with me and put it here. Okay, so this becomes equal to, then I will have 1 over 2 square root of u, which is this one, but it is not finished. I have to multiply by u prime. Yes? Are you with me? Yes? Okay, and then this is very simple. What is the answer to this one? Is just simply 2x. And then you see that I have a 2 here and a 2 in the denominator here. So I cancel those 2's out. So 1 is left and x is left from here, and square root of x squared plus 1 is left. So let me just write it down. I copy and paste the first part. It's x plus x square root of x squared plus 1. And then multiplied by 1 plus x over square root of x squared plus 1. Okay, by the way, differentiation process is finished now. But my goal is to achieve to this function, which I haven't apparently. Yes? Do you have any idea? Either the problem is wrong, or I have to simplify it more to be able to get this one, because my goal is to show this equality. So do you have any proposal or any suggestion for me? So if you don't mind, let me copy and paste and take it with me to the next page. We don't have enough time, space here. So copy, we go here and paste. Okay, I want to wait for you now. Can you tell me how should I continue? I can guarantee the problem is not wrong, so you should be able to simplify it in a way that it reaches to that expression, simple expression 1 over x square root of x squared plus 1. By the way, in mathematics you don't need to see everything in detail until the very end. So what is your guess? Immediate guess, more or less, yes?
We just multiply.
Okay, so one immediate guess is multiplying, but I will not do that. Why? This comes to my mind as well, by the way. So I take this one and multiply it here. So I will have this expression, but the point is that I also have to suffer a little bit even more to multiply that here. Yes? So the first thing comes to mind is multiplication. But because of that, be careful. If you want to be a good mathematician, be lazy first, okay? So don't do that. Okay, then what to do then? The first natural idea didn't work. There is another natural idea. These are the only natural ideas. The other natural idea is let me ask you, because you know that, okay? I don't know, for some reason you don't learn this. I write 2 and I write 1 plus 1 over 5. Okay? And there are 2 natural ideas exactly here. One natural idea that Rocco mentioned is doable here because they are simple numbers. I don't say this is wrong, but it was harder for this algebraic expression. There is another natural one. What's that?
Add them together.
Okay, so why do you answer it here in this context more or less immediately, but you cannot answer it? This is the only thing that you need to teach yourself. I'm just drawing your attention to it. Because if you didn't know, you didn't even know this one. But if you know this one and you don't know the complicated one, you need to teach your brain how to think. And that's it. Okay, so the next one is to take the common denominator, to add them up, yes? So what we do, we just write 1 over x plus square root of x squared plus 1. And then I hope that now you know how to take the common denominator. For example, what is the common denominator between this one? Because the denominator here is 1. The denominator here is this one. Between these two, what's the common denominator?
The second one.
The second one. So this is square root of x squared plus 1. And I hope that you agree with me that I can write this. This is very strange. These days, this iPad is acting very weird. I don't understand what the problem is. Do you have any experience of this? So let me clean that one as well. Okay, so what was I? Okay, so this is a square root of x squared plus 1, and then I have x. Do you agree? Okay. Okay, then what? By the way, if you want now, I can remove the pair of brackets and put a dot here. That's enough. And what should I do? Is that clear now? Yeah, they take each other out. So this, whatever it is, it's exactly the same thing that appears here. Of course, here is x plus a square root, and here is s square root plus x. They are the same. And what is left for me is exactly 1 over square root of x squared plus 1. And that's exactly f of x. That's the end of the problem. Okay, so, but again, I want to draw your attention. Finding a primitive function is a different story. And by the way, for understanding how to find this primitive function, you have to wait for the university. So we will not study that, even though the function is very simple, 1 over square root of x squared plus 1. Another thing, another surprise that I want you to know immediately is that this is not possible to get a primitive function for every function. Okay? Okay, let me elaborate on that. You might say that, okay, the function should be very complicated. No. The function even is very simple. So for example, let me just try to describe this. Okay, so here, if I give you a function of e to the power of x, might be there is something in here interacting. No, there is no method or something. Anyway, so if I ask you, give me a primitive function for e of x. By the way, what is the meaning of this question? I am asking a primitive function for e to the x. I mean, can you give me a function whose derivative is e to the x? What's the answer? E to the x itself. So it is extremely easy to find a primitive function for this one. But let me just write it as e to power x squared and ask you the same question. Give me a function whose primitive, whose derivative is e to the x to the 2. You can test if you want. You propose something, I check if it works or not. But if you don't mind, let us not spend time on it. There are no primitive functions that you can write as elementary functions. What do I mean? There are some functions we know about. Polynomial functions, trigonometric functions, exponential functions, logarithmic functions. These are functions we know. It turns out that this is a hard mathematical theorem. You cannot find any primitive function for this very simple, innocent looking function, which is expressed in terms of known functions. There is no combination of logarithmic, polynomial, exponential, trigonometric functions in any case that you can imagine whose derivative turns out to be e to the x squared. This is one thing. I don't want to write them. It takes a long time. But the question is that, is there any function whose really its derivative is this? The answer is yes. But that we have to artifact the function. We have to artificially make a new function whose property is exactly this. And it is defined in terms of integrals. But that is what I'm saying. If the answer is that, is there any primitive function for this function? The answer is yes. But can you find a primitive function in the category of familiar functions, which is serving a primitive function for this? The answer is no. Okay? So what I'm saying, and by the way, is this function so complicated? No. If I ask you to differentiate it, in a matter of seconds, you can differentiate it. So that I want you to understand the problem of differentiation is completely different from the problem of finding primitive functions. This is something that you have to expect. And this is why in the university, you actually spend a lot of sessions to learn how to find primitive functions for particular functions which we know how to do it. Okay? That's what I want you to know from the very beginning. Okay, so let me also, let me go back here. I want to give you an interesting application of this remark. So what is the remark? This remark tells you that if the derivative of a function is equal to another function, is equal to the derivative of another function, either the functions are completely equal or they can differ by at most a constant. Okay? It's actually an important theorem. So let me also try to give you an example so that you can feel how we can actually somehow exploit this formula, this idea to prove some formulas, okay? So I would say that let x be a real number any arbitrary real number. Prove that, of course you know the formula that you're supposed to prove that sine x squared plus cosine x squared is 1. Of course you might say that here, I already know about this formula a lot. Yes, but if you remember, we proved the formula based on geometrical argument. I mean, unit circle and things like that. And the formula is so simple that you could use those formulas. But there are many formulas like this, that we have a function on the left and a constant on the right, which is not that easy to prove. I want you to feel, how can I use this remark to prove it again that this is true, but in a different way. Okay, I want you to understand what I'm using, okay? That is according to that remark. So what I do, I would say that, okay, so I would say that let f of x be equal to this function. Yeah, don't ask yourself all the time, how should I know this? You probably don't know it because you don't have experience with that, but you will see what happens at the end. Let f of x be this and g of x be equal to 1. Okay? So I want to prove that this one is equal to that. What I did so far, I give this the name of the function f, and this is just a constant number, so I consider that's a constant function. Yes? Okay, so this is g of x. So what should I do now? I will differentiate them. So f prime of x. Okay, I want, by the way, practice a little bit how much you remember. If I ask you differentiate this, you should be able to do that immediately. What is the derivative of that? I hope that you are not making the common mistake. So what's that? Forget about this. What's the derivative of that? Yes, that's the correct one. Because people are usually in a hurry. They write cosine 2 cosine x. Yes, that's not correct. The correct formula, what I'm going to use is this formula. So we know that u to the power of 2 prime, what's the answer? It's not 2u prime. It is 2u prime. Yes? So now if I give the role of u to this guy, so I shouldn't be in a hurry to write 2u prime. I have to write 2u times u prime. So it becomes what? It becomes 2u, which is sine x, multiplied by u prime, which is sine x prime, plus the same story here. Now this time I give the role of u to this guy. It becomes again u squared. I will use the same rule. So this becomes 2 cosine x, which is u now, multiplied by cosine x prime. First of all, let me know that, is it understandable? Okay, but now do you remember the formulas? What is the derivative of sine x? Cosine x. And then what is the derivative of cosine x? Minus sine x. Okay, can you tell me what will be the final answer to this calculation? I'm trying to keep you alert, you know. 0, yes? That's 0. Why? Because that's the same combination. This is negative and that's positive. Yes, they add up to 0. So what I learned is that, therefore, the derivative of f prime of x is equal to 0. Yes? Now, if I ask you what is the derivative of g, I think it's a matter of milliseconds. Yes, what's the derivative of g? It's again zeros. Yes? So what I concluded that if I define the functions f and g in this way, the derivatives are equal. Because both of them are equal to 0. So therefore, f prime of x is equal to g prime of x. I didn't show that f is equal to g. By the way, my goal is to show that f is equal to g. Yes? This is f, this is g. I want to show f is equal to g, but I didn't do that. I just instead proved that f prime is equal to g prime. Can I conclude that, okay, because f prime is equal to g prime, therefore f is equal to g? Can I do that? No, because they might differ by a constant. Yes? Yes or no? Okay, so then it means that, what can I conclude from here? This means that there exists a c, which is a constant, this is important, such that what happens if f of x is equal to g of x, but not necessarily g of x itself, might be, it contains an additive constant as well. So if I want to write that, it becomes sine x squared plus cosine x squared is equal to 1 plus a constant. By the way, you have to think in that way. Assume that you really didn't know anything about sine x squared plus cosine x squared. This is a very notable progress, achievement. Why? Because we showed that sine x squared plus cosine x squared is 1, which is a constant, plus possibly another constant. It's a very important progress, because in principle, when you write something which depends on x, how we should know by changing x nothing will change, because it depends on x. But here this proves that. By this theorem we realize that whatever this is, it is a constant. Yes? But unfortunately I have an extra c, which is actually a little bit problematic here. How can I get rid of c? Because I know the answer is supposed to be just 1. So how can I get rid of c with a nice argument? Of course, the easy way is just to cross it over, yes? But that's not a nice argument. So how should I, by a nice argument, show that c is 0? Yes?
Could it have something to do with the fact that trigonometric functions can't go above or below above?
I would, even if it is correct, which is of course, but I don't want to use that. I'm just ignoring our trigonometric knowledge.
Okay.
I just want to use this to prove that this is exactly true. The reason is that if I know that this one is a constant, how can I say it? For example, let me see that if you can understand it. If I say a function is constant, what is the value of that function? What is one idea to find that value? I guarantee you that, okay, I have a function in my head. I guarantee you the function I have in my head is a constant function. Okay? And I give you one more information. I give you f of 7 is 10. What can you say about my constant function?
It's always 10.
It's always 10. Isn't it clear? If I guarantee you I imagine a function, I guarantee you the function in my head is a constant, and you might say that, okay, which constant is that? I don't say it directly, but I give you this information, f of 5 is 10. So what does it mean? It means the function that you imagine and you guaranteed is a constant, it should be f of x equals to 10. Is that right? Yes or no? Yes. So this means that if I know a function is constant and I want to determine the constant, I just need to calculate the function at one particular point. Whatever that number is, that is my constant. Yes. Now this is important. Now I know that this function is a constant. If I ask you, can you tell me what that constant is? You will tell me that, for example, let me calculate f of 0. If you want, you can calculate f of pi over 2 or f of 45 degrees or whatever, yes? I calculate f of 0. It gives me sine 0 to power 2 plus cosine 0 to power 2. What's the answer? What's sine of 0? Sine of 0 is 0, cosine of 0 is 1, so the answer becomes 1. Okay, now can you tell me what is c then? 0, because this is a constant. I calculated this constant at one particular point. Which point doesn't matter. I chose the simplest one. I got the answer 1. So this means that 1 plus 1 should be 1 plus c. So this means c is 0. And if c is 0, then I can get rid of c and then I get my answer. Yes? So this is an indirect way of proving things. You will see a lot of these functions in the future. So this is a very good way to prove identities, using derivative to show that two expressions are identical. Okay. Now we start the lesson. Okay, what I'm going to teach you?
Primitive function.
No, it's assume that you are a mathematician and now you want to give energy to this topic. So we talked about what a primitive function is. We are not that motivated yet. This is just a mathematical curiosity. By the way, mathematical curiosity is also very good. Sometimes it derives a lot of crazy ideas. Yes, you just want to find a rule. For example, there are, by the way, very nice rules about how to solve Rubik cube or something like that. So it's called coming from graph theory. So there is an algorithmic way probably to solve them. Yes, I mean that's just a mathematical curiosity. Yes, that's just a game. So don't underestimate the powers of games and stories in our lives. They are very powerful. Okay, but now we know that for some reason we are interested in the topic of primitive functions. What I have done so far, I have defined the concept for you. Okay. Okay. If you are a mathematician and you want to set up the theory, what do you do next? What question you ask yourself to be able to answer? Because, by the way, these are important questions, you know. I am your teacher, I can teach you, you can learn. But that's not the idea. You need to practice critical thinking. Assume that you are at the top of the research. No one knows what's going to happen, so you need to ask the right questions from yourself. So what should I ask?
So like we did with derivatives, where we made a table of different functions of the derivatives, we do the same with primitive functions.
Yes, more or less correct. So you are addressing this question: how can I find this damn concept? Yes. If you give me a function, how can I find its primitive function? Yes. So this is. And then you remember what we did in. We had two different kinds of rules in differentiation. Can you elaborate on that? Two types of formulas. I hope that you understand what I mean.
Oh.
Yes.
Do you mean like the definition of the?
No, that is the definition. No, but in the formula sheet you have two types of formulas when it comes to the concept of derivative. Yes?
Do you mean like one, if there's a set function, this is how you differentiate it, and the second is different stuff like chain rule and
Exactly.
rule?
Exactly. So we have some generic rules which we can apply to all sorts of functions. Let us name them. One of them was the sum rule. What does it mean? If I know the derivative of f and g, how can I find the derivative of f plus g? The answer was so simple: f prime plus g prime. The same answer for f minus g. The same rule for multiplying a function by a constant. And then we learned 3 more rules in Math 4. And by the way, that is the end of those kinds of rules. Yes? The rules, yes, are what? Are product rules, quotient rules, and the king of them was the chain rule. I mean, if you go to the university, you will not expand those rules, but you will expand other type of formulas, which is the table of functions.
So there are no more of the other
Generic rules now. These are the only ones, and we don't need more than that. Do we?
All the rules as like all the ones we know, or like it's proven that there are no more rules?
No, let me think about this. Let us analyze the question. What's the meaning of question? We don't need more than that. Because every type of functions we have are either the addition, subtraction, multiplication, or quotient, or composition. These are the type of functions. But the point is that might be there are some functions you don't know about. Yes? So that is not a generic rule. It is the derivative for that particular function. So I mean that in the university, no new general rules will be added. but the table of the derivatives will be expanded because you will learn about new functions. Yes?
I guess what I'm saying is, like, in the future, theoretically, if we find some new, completely different type of way to put together functions.
Yeah, might be. This question is more or less the same question that what happens if I add a new arithmetic rule to my algebra. So we have powers, addition, subtraction, division, things like that. You might say that, okay, in the future I want to add a new operation to my arithmetic. Of course, if you add that operation to your arithmetic, it will translate itself to a new generic rule for derivatives as well. That is the same type of question. And yes, if you add a new, by the way, you can define operations, but yeah, you can define any kind of operations that you like, and in that case, it gives rise to a new generic formula for the derivative as well.
So it's more that, but I don't know if this is a relevant question, but why have we only decided on 4 operations, like addition, subtraction? Is there like no use for any more types of operations? Like, can we do everything we want to do with these 4 operations?
Yeah, apparently yes. Yeah, apparently yes.
So,
yeah, but we can define them. For example, I can just write something here. For example, I can define a star operation acting, but a little bit weird. I can say it's a squared plus b. So whatever I put for this star operation, it acts like that. So either this combination is so useful that I will try to understand and tabulate the properties of this star operation, or I just leave it go, okay? So far, that's exactly that. Okay, so we want to do this. So I need, again, 2 types of generic rules and table of formulas. The generic rules are even more limited when it comes to primitive functions. We have only 3 of them. Yes? So let me just write them. For some reason, the book doesn't take this for granted, but it is not trivial at all. Okay, so let me just write different primitive, I mean, how should I write that? Primitive rules, okay? Primitive function rules. And I would write generic, probably, rules. Okay, so, and then I invent a new notation from myself, so I would say that the reason is that you don't study the integral sign at this level, but let me just use this notation. So I would say PRM for primitive. My claim is that primitive function of f plus g is equal to the primitive function of f plus primitive function for g. For some reason, the book takes this even in matrix and even in Math 4, it takes it for granted. But that is not trivial. So number 2 is the same thing. Let me just not repeat it. Plus or minus, it works for both of them. And then there is one more rule, primitive of a constant multiplied by a function. So let me emphasize constant. And let me emphasize here, that is the product, yes? Multiplication. So then what happens, do you remember from Math 3C? What's the answer? If I have a function multiplied by a constant and I am interested in the new combination, what can I do?
Was it the constant?
Yes, it's a constant multiplied by the primitive function of my function. Yes? Okay, so let me also write this as a remark. I don't know, even though every time I mention this, but I see every now and then people make mistakes. Okay, so remark. Okay, so there is no particular rule for the primitive function of the product. There is no particular rule for the primitive function of the quotient. And if you believe that this should be primitive function of f multiplied by primitive function of g, I warn you that's wrong. So I would say that it is a very good idea to write them and cross them over. Okay? So the rules are quite limited when it comes to this. Okay. By the way, let us prove one of them. For example, if I ask you why do you think this formula, for example, with the positive sign is correct, so I would prove it like this. I would say, for example, let a primitive function of f, I give it a name capital F, and let, for example, primitive function of g, I denote it by capital G. We prove that primitive function of f plus g is equal to capital F plus capital G. Okay, take your time. Do you understand? If I prove this, I am done. Yes or no? I want to prove this one for the plus sign. I gave the name of capital F for this to write simpler, and I gave the name capital G for that one. Do you agree if I show this I am done? Yes? Because what is this one? This is just F. And what is this one? This is just G. And what is this one? This is primitive of F plus G. If I can show this, I am done. But now, how can I prove this? Exactly like that example. If I propose you a primitive function and I ask you to show it correct, what do you do? I am proposing, by the way, you see, I am proposing primitive function for this is that. You want to confirm that. How do you confirm that? Okay, answer quickly. Yes. Yes.
The definition.
So how? You throw me the question on me, okay? Just give me complete, concrete example, as if you are the teacher. I give you a function, and I propose you a primitive function. How do you confirm that?
You find the derivative.
Yes. So why don't you say that? I find the derivative of what? Of this one. And show that the derivative of this one is f plus g. Do you agree? I want to show this. I have proposed you a primitive function for little f plus little g to be this. I want you to confirm that. To confirm that, you take the derivative of the proposed function and show that it is equal to the original function. Yes? So that is, by the way, if you understand that, that's extremely simple. So, to prove this, I need to ask myself, is it true that this is equal to f plus g? If the answer is yes, I am done. But you know a sum rule for derivatives, you know. What is the name of this one? This is the sum rule for primitive functions, but what I am using to prove it, I am using the sum rule for derivatives. It becomes f prime plus g prime. But what is f prime? What is capital F prime? F. And what is capital G prime? G. So we are done. As simple as that. So because of this, the book is taken for granted. It is simple but not trivial. There is a difference between simplicity and triviality, yes? Anyway. Okay, what I'm going to teach you next?
The second one.
No, the second one I put it as you, so you prove it yourself. But what is the next topic? No, I told you that so there is no product rule for primitive functions, there is no quotient rule. And there is something similar to the chain rule which you don't study. Yes?
Subtraction.
No, subtraction is the first one, plus or minus. What I'm going to teach you next. You remind me of Nemo in No, that blue fish, you know. What was that? That Dory, yes. You just told me. Yes, Rocco just told, yes. I told you that we have two type of rules, generic rules and then tables. So the next lesson is tables, yes? Yes, okay. So now you really
I'm sorry about like it's Friday.
yes, but I have also tested you on Mondays as well, okay? Okay, so anyway, so we want to start at starting setting up my table. Okay, so what's the first thing you do? You're a mathematician, you want to set up your table. Where do you start from?
Constant.
Constant, because these are the simplest possible functions, yes? Okay, so let me just, by the way, I don't know which color do you like, so, okay, purple. So I don't know purple and black is good or not, let us see. Do you think it's good?
I think it works.
Okay, works. Yeah. Okay, so I will keep it for you. I don't like it that much anyway. So I put the purple here, and then I want to set up a table now. Okay, so do you remember in the case of derivative, do you remember I had f here, f prime here. But in the case of primitive functions, what do I have? Here I will have still f, but what do you have on the right?
F prime? Or F?
No, f prime, big F, yes. So I have it this way. And you told me start with a constant. You are right. I start with a constant. What can I call the constant? I think, let me call it k, a constant. Okay, by the way, this table is mainly guesswork. Okay, but you might think that is a weak way of doing mathematics, I agree, but it will be more valuable than you think right now. So I am asking you to give me capital F for a constant function. For example, if I give you k is 2, I ask you to find capital F. What do I mean? I mean give me a function whose derivative is 2. What is that function?
2x.
2x. If you give me 3, what's the function?
3x.
3x. But if you give me k, what's the function?
Kx.
Kx. Yeah, so that's very easy. Now I hope that you agree with me. Kx, the purple is not working fine. What is it? Okay.
You can change to pink.
Yeah, let us do that, okay? By the way, it's a Friday, it's better to play a little bit. So, a color, which one do you prefer? This one. Oh, it's more better, yes?
Yes.
It's better. Okay, and then I have a constant here. A constant is, I show it with capital C. And you know that this capital C appears all the way down in this table, yes? Because we just learned about it. Okay, after the constant, what is the most complicated function we have after the constant? X. Okay, but if you don't mind, let me ask your guess about it. I will write and I will clean it later. So can you give me a function whose derivative is x?
1 over 2x squared.
1 over 2x squared, yes? Why did you put this 1 over 2x squared? Because you anticipated what is going to happen. If you don't put this there, and you differentiate x squared, what do you get? You get 2x. X part is good, but you don't want to have 2. So you put this 1/2 in anticipation what is going to happen to cancel that coming 2. Okay, now can you tell me what happens if I give you x squared this time? No, because the function should be of the 3rd degree, yes? Because you want to have a 2nd degree after differentiation. But if I just stop here, it is not working, because if I differentiate this, it becomes 3x squared. And I want just 1x squared. So in anticipation of that, I should put what?
1 over.
Yes, I put a 1 over 3 to get that one. So now let me ask you this question. Can you, because that's more or less the guesswork. So what do you think if I continue and I reach to x to power a? So what can you say? 1 over a plus 1, x to the power of a plus 1. Yes? So this is the formula that I want to put there. Of course, be careful. I have sometimes seen that the students confuses 2 tables. In the formula sheet, you have 2 separate tables. Primitive function table, derivative table. They are very similar, but they are not identical. Okay. It becomes 1 plus a, x plus a. And then, of course, you know that I have to add a constant. Okay? Are you happy?
Yes.
You shouldn't be.
No.
Yes? Why you should be happy? Something is disturbing you, even you don't know. You should know that. What is disturbing you?
Plus C.
No, plus C doesn't disturb me. If plus C is disturbing you, you should be disturbed all the way up to the end of this table. Yeah. Yes, Alexander?
It is -1.
-1. Every mathematician knows by heart there is some problem if I have a fraction. And you have to be sensitive. Yes? You need to train your nose for it to smell bad things going on. Yes? And bad thing in mathematics doesn't mean any war or something. It means division by 0. It's a catastrophe in mathematics. Yes? Yeah? Okay, so what you are supposed to do, the problem is that we didn't solve the problem in full detail. So we answered all possible powers except -1. Yes? But should we throw that away, by the way? No, that is also an innocent function, yes? If I ask you what is f of x equals to x to the power of minus 1, what's the answer? It's just 1 over x. By the way, you ask GeoGebra to draw the graph, it will generate this one. So it exists. We cannot just ignore that. Yes? Okay, so it means that we should answer that question as well if you want to complete. That was the end of the problem in Math 3C. We didn't answer that question. We want to answer this question this year. What happens if a is equal to minus 1? Should we give up?
Yes.
Okay. Yes? But if we decide not to give up, then? So the question is now, can you formulate the question for me? No, you should be able to formulate. Either you should solve the problem, I will bring my gun now out, yes? So either you need to formulate the question or you need to answer.
How would we find the previous function for x to the power of minus 1?
Which is more familiar to us in the saying 1 over x.
Yeah.
Exactly. So it means that what I want to put here, that is the question that I want to answer. But you already know the answer if you are not the dory fish, you know. What is the answer? ln of x. And that is the famous, so that's the function. This is why we couldn't talk about that in... by the way, in Math 3C we also learned about ln. I don't know why they didn't put that there, yes? Because we didn't know about the chain rule. Okay, anyway, so because the proof of that formula is going through the chain rule. So this becomes ln of x. Are you happy?
No.
Okay, so what is your disturbance now?
Wasn't that x cannot be negative?
Negative, thank you. So we add that one here. So now you are training your nose, yes? Good.
So what do we do when x is negative now?
So when x is negative now, then the derivative, can you answer that question? It is not in the book. For some reason they have restricted themselves to positive x, but that's a legitimate question. The answer would be simply ln of minus x. Yes? The derivative of ln of minus x, by the way, it's very interesting. What's the derivative of ln of minus x? This is a question to ask. Let us answer that. What is the derivative of ln of minus x? By the way, ln of minus x is defined or not defined? Is it nonsense?
It's also defined.
Is it undefined because you see negative sign?
Oh, it's only defined
For negative one. So it is still defined, but I have to choose x negative. So don't be fooled by just apparent negative sign that you see there. Yes. But so it is defined, but for negative values. But what is the derivative for ln of minus x? Please answer them very quickly. Why is that? Who said 1 over x?
No, I mean 1 plus minus 1 over x.
No, be careful. It becomes again 1 over x, but why?
Intuition.
No, intuition doesn't work. That's good for fiction.
X is negative. Negative times.
No, what I told you about, we just had this formula. You see, I am proving the Dory attitude, you know, several times in 1 minute. Yes? I hope that you agree with me now. So this is the formula we use in the second example, you know. So what is the derivative of ln of u? Is u prime times divided by u. So that's also working here. And actually Hussein was very close, but he messed up himself. You know, the derivative of this one, which one is playing the role of u?
Minus x.
Minus x is playing the role of u. And the formula was ln of u prime is what? U prime over u.
Yeah.
So this becomes minus x prime over u. What is u?
Minus x.
Minus x. But what is the derivative of minus x?
Minus
Minus 1 divided by minus x. What is the answer?
1 over x.
Is again 1 over x. So it is interesting. So the derivative of ln of x is 1 over x. The derivative of ln of minus x is also 1 over x. But is there any difference between the formula? By the way, this is another very interesting example. The derivative of ln of x is what? 1 over x. And the derivative of ln of minus x is also 1 over x. Do you feel uncomfortable now? You should feel uncomfortable. Yes? You're happy? Yeah, that's good. But you shouldn't feel happy now. Something should disturb you now. Let me just try to, you can have some fun, you know. So ln of x prime is what? Yes? And then ln of minus x prime, no cheating, I am completely honest here. Both of them are 1 over x. I can conclude that ln of x prime is equal to ln of minus x prime. Okay? Are you happy?
No,
Why not?
because it was undefined before.
No. By the way, if you say I'm not happy, you should give me the reason. You cannot go to a psychologist and say I'm sad, but they ask you why. I said that no, I don't know. But you should know, yes? Why you shouldn't be happy now? I mean, you should be happy, but you should be disturbed. Can you see why? Okay, let me ask you again. If I give you f prime of x is equal to g prime of x, what is the conclusion I told you that can make up? We also spent 15 minutes to solve a problem with that, yes?
Differ by most an additive constant.
Okay, so are they differing by at most an additive constant? That is the disturbance. Yes?
No.
Because one of them is ln of x, and the other one is ln of minus x. Do you think they differ by a constant?
No.
No. So what the problem is? The answer is simple. I lied to you. I didn't lie to you. I didn't write it down. I told you that. Do you remember? I told you that when I was teaching you, there are some complications in this formula, and that is that they are defined on the same interval. If they are defined on the same interval, and if this, then everything is correct. So mathematics is sensitive, really. So you have to be careful.
In this case, they're on different intervals.
Yes, one of them is defined for positive values, the other one is defined for negative values. So it is not a contradiction. If this is, by the way, if you find one of these problems in mathematics, then whole mathematics will collapse, and then you get relieved. You don't need to do the exam anymore. Because there is no mathematics there, yes? So mathematics can tolerate everything, hardness, softness, but it cannot tolerate even one contradiction. Yes? And by the way, this is also a big lie. Because Kurt-Gödel actually proved that we cannot disprove or prove anything based on the finite number of axioms. So it means that, by the way, you might didn't know about that. You have to be waiting for a paradox coming in at some point in mathematics. Then either whole mathematics will collapse, or mathematicians try to solve a problem there. Then they have to add more axioms. But the point is that it doesn't matter how many axioms you put in. It's always a paradox lurking for you. Okay, so that's a big philosophical impact in science actually coming from mathematics. Okay, but let me now, so you now, the problem, this is a disturbance, but the disturbance is solved now, yes? Because the right version is not exactly what I said. The part that I orally mentioned, I didn't put it in this because that's not at the level of your course, yes? But anyway, so be careful about these minor things. By the way, they are not minor, they are very major. Okay, so let me clean everything. And then, okay, so we continue now. So that was your question. This is why in university texts you don't see the formula here. By the way, what do you write if you go to university instead of these two? If you want to summarize all what I did. Okay, so in the book they have written only this formula. But if I want to insist to drop this, can you write another formula for me? You learned everything now. I want to see how mathematicians you are. Yes?
Maybe the x is valid.
Exactly. So if you relax x positive, this is why I prefer, I think in the previous years I actually wrote this. When I wrote this, that is working for both positive and negative. Yes? But for some reason the book has chosen this one, so let me stick to the book. Okay. So, okay, then what? Then what? We had another type of functions. You also studied in Math 3C what that function was.
Trigonometric.
No, trigonometric we learned this year.
Oh, yeah.
So if you want to go in order, to don't mess up exponential functions. Yeah. So do you remember what was that? So this one, let me put an arrow here. This is new. Okay, and now we go to the next one. This was also not new. E to the power of kx. Can you guess me the formula? I need a function whose derivative is e to the power of kx. K is a constant. What that is?
1 over k.
Yes. I hope that you understand why we put 1 over k. Because if I ask you to differentiate this, do you know that there is a k coming down? But you don't need that k. So you need to anticipate for that to get rid of it. How do you anticipate? By putting an extra factor of 1 over k, that it will cancel the coming k, the k coming down. Yes? That's also correct. Okay, now today we have 2 new formulas, yes? One, what is coming next? What Roku actually mentioned, yes? Trigonometric functions. And then there are 3 of them. Unfortunately, one of them is not according to your lesson in the table, so you have only sine and cosine, yes?
Don't we have 8 here?
Yes, if you want, that's a very good question. Let me also write that one. Do you remember that one? So a to the power of x. Let me write that. If you want, this is... it is. So do you remember what is? Let me write and clean it. A to the power of kx prime. Do you remember what's the derivative? K goes down, the function repeats itself, but I have to also multiply by ln of a. Okay? So in anticipation of coming these 2 factors down, I have to put them in the denominator so it will be cancelled. So this becomes 1 over k ln of a to the power of k x plus a constant. But of course here a should be also positive. Okay, so let me write these 2 formulas and I wait for you for your guess. So this is one of them. The other one is cosine. I will also teach you a little bit about tangent later. It is not hard. Yes? Okay, can you tell me what can I do now? What is the formula for what is in front of sine kx?
Minus cosine.
Yes, it's very good that you put the minus sign. Good, good. Because in derivative sign, the derivative of sine does not include a negative sign. It includes positive cosine. But here I want to find a function whose derivative is sine kx. So I have to write minus, and then I have to put cosine kx. But is that enough?
Minus 1 over k.
Yes, exactly. Thank you. So you understand what's going on. It's minus 1 over k cosine kx plus c. Then I hope that you can also see what is happening here. What is that? 1 over k with positive sign, sine kx plus c. Okay, I want to add something here. I want to see how many of you remember. Okay, so I write 1 over cosine to the power of 2x. Can you give me a function whose derivative is 1 over cosine squared x? Yes? Tangent. But it doesn't mean I solve a problem, because why I didn't solve the problem yet for tangent? Because I want to have the tangent. I want to have the tangent on the left side, yes. Yes, so this is not the solution for the tangent. I solved this problem for 1 over cosine squared x. That's also, by the way, a function. The name of that function is secant squared x. Yes? Okay, so that's also something that you already did. So we got something for free. So let us put it there. Okay, but up to here is, I think, in the formula sheet. Okay. So let me start with one example and then we will finish it. Okay. So example. Okay, so by the way, let me introduce you some things. So here, let me write. There are differences about articles. Sometimes we say all primitive, sometimes we say a primitive, sometimes we say le primitive. Okay? This is also important to know about. So, what is the difference between these? Yes?
If it's all, we should write plus C at the end too.
Yes, so it means that you need to show me that you are respecting the word or by putting a C there. If I say
Then any constant.
which is the best one? 0. As of course, if you write 1, doesn't matter. But when I say there, it means,
Maybe there's only one.
which means that it is not possible unless I provide you with extra piece of information so that you can use that information to fine-tune the C. Okay, so these are the differences of articles that you use. And then, by the way, I like glasses, yes? It shows that I like I'm a doctor or professor, you know. I'm just taking it off, saying something, putting it back, writing, you know. I have the feeling, yes, I am a great man now. Okay, so let me write, find, so you understand the differences. So for making life simple, so I would say find a primitive function. A primitive function, and of the following functions, of course, yes. So number 1, let me write that f of x is equal to 3x squared plus 5x negative 7. So I want to find a primitive function for this. So how should I do that? I want you to understand, even though in the book it is not mentioned at all, but they are using the rules. Which rules are involved here? You have addition, sum rule, subtract rule, or difference rule, or I don't know what's called. And then you have this number multiplied by my function. Even though you write it quickly, but I want you to appreciate that you are using all those rules. Okay, so I write a capital F, and what I do, I have a constant multiplied by my function. I keep it like this. I don't touch it, but I take a primitive function for x squared. I refer to my table, I see the second row, and then in the second row, instead of a, I put 2. Okay, so what happens? It becomes 1 over 2 plus 1, and then x to the power of 2 plus 1. The same story here. I have the sum rule, so I go to the next one, I take 5 out, and then I give the role of a to 1, and then use the same formula in the second row. So it becomes 1 over 1 plus 1 x to the power. I don't write it like this, but this time I want to write it so that you understand. So what is 7? What can I do with 7? What's the answer? Which row is useful? Which row is useful? The first row, yes? So what is the answer to minus 7? Minus 7x. And then of course I always prefer to simplify. So this is 3 and that is 3 are gone. This is also 3, so this becomes x to the power of 3. And then it is 5 over 2 x to power 2 minus 7x. So that is a primitive function for this, yes? And by the way, let me also write, this is new. This is new. And this is also new. Okay, let me also write another one, and I think that is good. We stop here. I will, of course, this lesson is not finished, but let me stop here. So if I give you this one, what is your suggestion for me? If I give you, for example, I don't know, 5x squared minus 3x plus 1 divided by 3x squared. By the way, I want you to draw your attention to this. I found all these tables more or less by guesswork. Yes? And even in that case, it was not that hard to guess. But I hope that you agree with me, this is not that easy at all to guess a function whose derivative is this function. So I just want you to understand we are doing more than guessing. Even though we started with some educated guess for all these formulas, but at the end, we are more powerful than we are thinking, yes? Yes. So how can I understand the primitive function for this? Yeah, try to impress me. This is the last problem. Before having a nice weekend, yes?
Can you maybe make it this truth.
Yes,
Yeah,
decompose.
divide them.
Exactly the same idea before differentiation. That's the same thing, yes? With the difference that in differentiation we had an alternative, that is the quotient rule, but here we do not have any alternatives. So we have to use this method that you described. So let us just do that immediately and then we are done. So f of x is equal to 5x squared divided by 3x squared minus 3x over 3x squared and then plus 1 over 3x squared, yes? And I simplify that so it becomes 5 over 3, okay, minus 1 over x. Could I give you this problem in, okay, so this is the problem. So what I'm supposed to do? That is important. Just listen and then we are done. Okay, so that's good. Okay, for this one, which formula of this table is useful? Which row? The first row. That's a constant. For this one, which row? This new one, but I have to add that x is positive. Assume that these minorities, in the book, they are not sensitive to these details. But what about this one? It's 1 over 3x squared. It's not in the table. It is, but yeah?
You can switch it up.
Okay, so that's good.
Make the
So,
following.
okay. But do I need to do the same thing for this one? Do I need to bring it up as well? No, because for this very particular one, I have a separate row. Yes? So what I do, it becomes 5 over 3 minus 1 over x plus 1 third of x to the power of minus 2. And now everything is ready. Let us just write the answer. It becomes 5 over 3x. Instead of minus 1 over x, a primitive function is ln of x. Here, I have to write absolute value, but I am just following the book, okay? And then for the other one, I have 1 third x to the power of minus 1, because I have to add this time, divided by 1 over minus 1. Do you agree with me? Yeah, sorry for the mess, but let us try to have a little bit of journey here. Okay, so what is the final answer? F of x is equal to 5 over 3x minus ln of, I don't know, I have a bad feeling not to write absolute value, so let me write. Okay, and then that becomes minus 1 over 3x. Do you agree with me? What I did, this is just minus 1. I multiplied here, it becomes minus 1 over 3, and then I brought this back again, so I got that one. And because it is mentioned a primitive function, I'm not sensitive to put this. By the way, you shouldn't put that, because then it means that you don't understand what's the difference between A and O. By the way, and now I hope that there is no way probably for us to guess that this function is the culprit, yes? Is the function whose derivative becomes this function. Okay. Any questions? No? No. Thank you very much.
I have a question.
Yes?
Why do we not learn about the reverse chain rule?
No. What do you mean by the reverse chain rule?
Isn't there like when you want like a rule for the chain rule, but for when you integrate?
No. There is that substitution method.
Yeah, okay, substitution.
Yes, but for ask the people who designed the curriculum. Yes. Okay. No questions? Thank you.